Investigating resistive forces. What are resistive forces? Resistive forces include friction, viscosity, and drag forces. These forces oppose the motion between two objects, thereby reducing it.
The broad purpose of this experiment is to determine and explore the relationship between resistive forces and velocity. More specifically, the relationship between the force of viscosity of a solution and the velocity of an object moving through that solution.
So far in our model, we know that objects in a solution will experience a resistive force, and energy will be conserved because we defined our system as including liquid, earth, and the ball bearing. Terminal velocity is the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. If you look at our free body diagram, the forces going up and down are unequal, but if acceleration were to equal 0 at the terminal velocity, the forces up and down would become equal. Newton's first law states that an object in motion will stay in motion unless acted upon by an outside force, and we have a resistive force acting upon the object in this situation.
Our purpose is to determine how changing the viscosity of a solution affects the velocity of which a metal ball bearing travels at.
These are the materials we used in our experiment. The three solutions we used were water, isopropyl alcohol, and dish soap, and we used metal ball bearings that were 8.43 grams.
Here's the procedure we used. We used the same metal ball bearing to reduce error from variations in weight. Also, we always started at the 50 milliliter line and tracked the ball until the first bounce. One of the very big concerns of our group was that if the beaker will be long enough for the metal ball bearing to reach terminal velocity.
Here are the position, velocity, and acceleration graphs in water, in alcohol, and in soap.
These are the equations we used to output values. The equation used to calculate the force of viscosity was dependent upon if the ball was allowed to reach terminal velocity or not. If the ball reached terminal velocity, such as in soap, the force equation used was force of viscosity equals -6 pi mu rv. If not, we used force equals mass times acceleration, and we used the acceleration over a period of time, or the average acceleration near the end of the drop. We looked at the acceleration graphs for both soap, alcohol, and water, and tried to find the most constant part of the acceleration graph to use for that value.
In our results, we found that alcohol had the fastest velocity and soap had the slowest velocity, while inversely alcohol had the lowest force and soap had the highest force. All values are negative as we define down as the negative direction. Here are the bar charts that also represent this relationship. When there is a higher viscous force, there is a lower velocity.
According to our data, it can be concluded that by increasing the viscosity of the solution, or increasing the resistive force on the ball, the velocity of the object falling through it is decreased. This is shown by the ball bearing falling in soap having a slower velocity when compared to those in alcohol and water. Therefore, viscosity and velocity are inversely related.
Using the forces in our data tables, we were able to solve for mu, the proportionality constant, as shown below. To find mu of dish soap, we knew that terminal velocity was reached, so force of gravity equals force of viscosity. To find mu for water and alcohol, terminal velocity was not reached, so we solved for mu with the equation F net equals mass times acceleration, which equals force of gravity plus force of viscosity. Due to the limitations of not allowing the ball to reach terminal velocity, these values of mu do not hold a true qualitative value, however, remain true to the relationship previously found. A smaller mu leads to a smaller resistive force. The relationship between viscosity and velocity hold true for all velocity before terminal velocity is reached.
Similarities between macroscopic friction and resistive forces such as viscosity are that both macroscopic friction and resistive forces perform the same function of opposing the motion. Some differences include that there is no static friction present in viscosity, and in friction from viscosity, there are many molecules acting on one object, whereas in macroscopic friction, there is one object acting on another.
Error can be sourced where it was difficult to track the object in tracker, since the object was moving so fast that in some frames it became almost invisible. In addition, the test tubes were not long enough to allow the ball in alcohol and water to reach terminal velocity. Lastly, we did not start the video process right when we dropped the ball, so velocity we recorded for the first frames were all 0.